superintegrability in unitary matrix models, please.
Jeszcze proszę. No,
45 minutes.
Видел, что все начинают доклад с английским языком, и потом надо что-то делать, поэтому я решил новое сделать. So my talk will be in English. And thank you so much for the opportunity to give a talk here. I came here last year and coming here this year also. So here. My talk will be on based on this paper with Alex Morozov about the superintegrability in unitary matrix models. So many people have their own definition of superintegrability. So I would like to define it as a kind of polynomial expression, and unitary matrix models is just like an integral over unitary matrices. So if you have an integral over unitary matrices, which we call matrix models, we can express it in terms of polynomials, which is superintegrability. So in this talk, I choose a concrete example of matrix models, which is called the Super model. So the plan of the talk is the following. We will first look at the motivation, so why this problem is interesting and how one should approach it. And then we will look some example for the super correlators. And we use two methods to solve this problem. The first one is solving linear equation, and the second approach is the Schur polynomial expansion. And then we say a little bit about the word identities for this model, and then about the future direction which can be done from this system. So first of all, the model was inspired by from the study of Vladimir Kazakov and Alexander Migdal, which is known as a Kazakov-Migdal model. If you have this particular kind of lattice, and in the sides there is phi, which is a Hermitian matrix, and in the links there are U, which is unitary matrix. Then the partition function of this model is written like this, where A is same formula. As you can see that if you put a's over here, then the partition function has two integrals. One is integral for the Hermitian matrix phi, and another integral is for the unitary matrix. So the model says that if you take this two kind of integral, then take quantum limit of this lattice, it will produce some induced quantum thermodynamics, induced QCD. But unfortunately, in the main paper of Kazakov and Migdal, they just like conjecture it and later maybe prove wrong or something like that. But regardless of their model, this particular integral is interesting to us from the general point of view. As you can see that there is a unitary integral there. So we are interested in this particular kind of integral, which you can see like there are a lot of this kind of integral over here. Yeah. So you see that this integral appears in the problem of lattice gauge theory, but previously this particular integral has been studied by Duksin and Zuber, Harish Chandra also. That's why this integral is called Duksin Zuber, which is to us is interested from the point of view of standard non-derivative QFT. So you can ask in general question that you can ask in standard QFT, like what are the observables, like the correlation function, and so on. But as you see that to answer all these questions, we need to come back to the problem of evaluating this particular integral. And when you want to evaluate this integral, you need to take integration of our unitary matrix. Now, if you can think that if this n is large, there will be a problem with integration using the standard integration technique. And it will be very boring also because big formulas will come from this DU, which is a hard method. So we wanted to do a different approach to calculate the correlation function for this model using polynomials, true polynomials. First of all, let me introduce what is known for this integral. This integral can be expressed in two ways. One is the determinant formula people found this at the random ones like this. Another approach is this one. So this particular integral you can express in terms of these two polynomials. So you can definitely, if you think that n is a 2 by 2 matrix, you can easily calculate this integral and check that this integral, this formula is consistent with this one, or for simple case. But if you go like n equal to 3, 4, 5, then it will be a bit harder. So our goal is to find this kind of formula for the correlation function. What we know about the correlation function. So this is a standard definition of correlator in integral form. So you just write this matrix element over here, this. And this has been studied back in 1992. Morozov developed a kind of determinant formula, which is this big formula over here, where A is a coefficient like that. And you can try to calculate for a big matrix using this formula. But there is also a problem that if you have, for example, 5 by 5 matrix, this formula will require you to calculate 120 exponential. So it's also not so pleasant, this formula. So we try to do further generalization from this one. So that's why, as you see that we actually try to find this analog of this integral. So integral formula for this correlation function, 2-point correlation function. We used two approaches. First one was differentiating this integral. So this integral is actually equal to this. So if you differentiate by the matrix element xij, it will give you this kind of sum in one side, and on the side is the differentiation of the polynomial by xij. You can do the same thing for this by ykl. It will give you something like this. So as you see that you have two such kind of expression. So now you can think about a simple example. For example, n equal to 2. You can put all these elements over here, and you can see that you get this particular system of equation. Now it's easy to solve. It's kind of a linear equation, and you can easily get the expression for this correlator and this correlator. And this is exactly this formula. So we see that there are some differential of Schur polynomials over here, and we also found that by numerical analysis, this correlator is same as this one, and this is same as this one. So they are both the same, and they have this kind of particular value. So we thought that okay, we found some interesting results. Now we can try to generalize this solving linear equation technique for n equal to 3. But when we move to n equal to 3, we have got this particular system of equation. So as you can see that they have total 9 correlators, so it means like 9 variables, and we have only 6 equations. 9 variables and 6 equations. So it's unfortunately we cannot solve this system. So that's why we are trying to find if any of this correlator is same as others. So are there any symmetry relation between the correlators or not? How can we check it? To check this, we need to calculate the correlator from this big formula, from this big formula for n equal to 3 by 3 matrix. And it was like a bit so it's not working, but okay, so not a problem. So somehow it gives a big formula, but you can still try to calculate it. And we calculate all these correlators and found that there is no direct symmetry between the formulas. So you can find this correlator, which is directly not equal
Что думаете, что там что-то произошло? А у вас если на компьютере видно?
Я не видно.
Надо заменить, компьютер не выдается.
Можно,
Даешь сигнал на проектор.
да, можно провод источник еще раз поменять, может быть.
Ты сейчас что-то дернул?
Ну, что-то там изменилось.
So we calculate all these correlators, and we found that no correlator is exactly equal to another. So it seems like we cannot solve this system, and this method is not working in case of 3x3 matrix. But they have this kind of symmetry relation, like if you change x1 to x2, it will give you this. If you change y1 to y2, so this kind of particular relation for off-diagonal, for off-diagonal mixed-term, and for the diagonal terms. So we need to think about a different approach. So the different approach we call it Sure expansion. So what is the algorithm of this approach? First of all, you take the formula, this big formula, and calculate the correlator from here, and then you write an ansatz for the correlator using some coefficients, and then you compare the both ansatz and your correlation function, and then you find the coefficients from this comparison. So how it looks like. So for example, in a simple example, we can calculate this correlator, which was previously I showed. Now you write an ansatz for this. So for example, we had an intuition that there was differential of Schur polynomials appears. As you also can see that this particular expression is not symmetric. So if it's not symmetric, you cannot express it through Schur polynomials because they're symmetric. So now we need to think about some non-symmetric polynomials. So what are the non-symmetric polynomials? Can be another possible option is the differentiation of Schur polynomial. So now you write this expression like this, and this T1y is the coefficients of this one. So it has some y and some numbers. So then you comparing these two equations, you can find all these coefficients from here, and now you ask the question: can I see a structure of the differentiation of Schur polynomials over here? And the answer is yes. You can see that this particular expression you can express like the following, like this. So then you put back all the value of T1, T2, and T3 over here, and now your correlator is exactly this. So you see that the execution of the correlator can be expressed in terms of the differentiation of Schur polynomials in a simple case like this. But there was a problem again that we tried to generalize this for higher EM diagrams. As you can see that this is only for this particular diagram, this 1-1 partition. So now what will be in case of like 3-0 or 2-1 or 1-1-1? And the sad news is that this idea is not working. I mean, I thought that we can continue like this with some other coefficients for higher terms, but unfortunately it's not working like that. So that's why we concluded that this particular approach can be concluded like this. Now, what do I mean by it doesn't work? What was the problem from our experiment in Optimal Mathematics? The problem was the following. In one side, you calculate the correlation function from the known formula. Another side, you write the ansatz, and then it gives you something kind of this kind of combination. One side gives you the combination of Ti, and other side is a combination of Y. This is from the formula, this is from the ansatz. And now we compare this combination and this combination, and unfortunately, and we solve the system and write the value of these TIs. But unfortunately, for higher EM diagrams, this system we cannot solve it. It doesn't give a solution, unfortunately. So that's why we thought that we can change this particular ansatz and think something different, so that the combination of TY would be different in the left-hand side. And then we could solve the system and get the value of this coefficient TI over here. So we change the ansatz and do a lot of experiments that how we can write the ansatz or to get a good to solve the system. And the thing we observed that there was actually, so in this case only one differential of Schur polynomials. But we observed that if we take second differentiation of Schur, then it gives us a correct answer. This is our final result of this whole study. We changed our ansatz and write it like the following way. So here, this P is actually when you have partition functions, when you have Venn diagrams and you write them lexicographical order. So it takes the R minimum is the first element of this lexicographical order, and R maximum is the last one. So, for example, for in case of partition 3, how many partitions we have? We have 3. We have 2, 1, and 1, 1, 1. So this 3 is the R minimum, and this 1, 1, 1 is R maximum. And then if you do this kind of choice, when the partition is odd, you do this. So for example, n is odd, n equal to 3 is odd. So you need to take this kind of choice. When n is even, you need to take this kind of choice. And if you combine these two choices and put it in this formula, it will give you a correct ansatz, which actually solve this particular system. So this is actually our final result that we got from the study. And then we calculated it, for example, so I personally calculated when the partition is 13, so it was like a big formula. So here I just demonstrate some examples. For example, when you have the partition 3, you get this particular ansatz. So this is the correct ansatz. When you have partition 6, you get this particular kind of ansatz in case of 2 by 2 matrix. If you have 3 by 3 matrix, you get this particular kind of ansatz when n equal to 4 partition. And then if you put this ansatz, then you can solve the system and you can find the correlation function. But as you see that there is actually a limitation of our approach, that we can get these coefficients from the determinant formula, but we actually didn't find a general form of these coefficients. So that's why we still need to depend on the determinant formula. If we get the general formula for this is, we can put it over here, then we can solve this problem fully. So that we can express our two-point correlation function in this model totally in terms of Schur polynomials. But as you see that we actually found this kind of we solved this problem when the EM diagram is small after 2. But when it's like more, then we need to think about it. So this is still an open problem. We are currently working on it. Then a little bit about the award identities. So as you see that the whole discussion is about two-point function, but we are also interested in calculation of n-point function. So there was an approach by Samson Satasvili back in 1994. He tried to do it, but his approach was completely different, and it gives also a big formula. He did it for n-point correlation function for this particular model. We also try to do this. So the main idea is to first think about what identities. If you can find it, we can easily generalize it to 4-point function, 8-point function, anything. So to do this, you can just try to continue differentiating this integral formula. So we differentiated. So this was the first differentiation, and the second differentiation gives you something like this. And if you differentiate the integral formula 4 times, it gives you this big formula. Now, if you try to differentiate again, it will give you another big formula. So the differentiation technique is actually not so convenient. And we found that we need to think about some different approach for this differentiation problem. So my scientific advisor, he suggests that we can try to think about some Feynman-like diagram technique, which is also called the tensor diagram for these indices, to deal with these indices. But unfortunately, in this particular study, we didn't include it. So it also needs some care that how we can develop such diagram technique for this kind of study. So there are still some open problems about this one. So the first and most important one is to find the coefficients in general form of Schur derivatives, and then try to implement our study for Schur expansion of higher correlators. And then we need to think about the tensor diagram technique that I just told you, and then find a full wire identities, which is still missing. And also we need to try to look for an approach to find the problem of the system of equations that I showed you in the beginning. That was all the whole study. So this is just a summary of what I just said. And that's it. So thank you so much. If you have any questions. Questions, comments, or anything?
So you haven't found any close format. I mean, you can...
Yes, we still haven't found it because
But how it looks like? I mean, these T's are what? These are polynomials?
Yeah, they are also polynomials, but they're very big polynomials in x and y. So we need to look at how this polynomial expression gives us something like this, some structured Schur differentiation. But in like a direct view, we just see that it's like arbitrary polynomials. And I didn't find any Schur polynomial structure or Schur differentiation structure, named Schur differentiation structure over there. So I think that it might like complicated structure, or maybe some differential with some free x and y's, maybe something like that.
Mm.
So we calculate these coefficients, but we didn't find any this kind of structure there. So it seems like we need to work a lot more about it. Yeah, we get the show.
I think you mentioned in the beginning of your talk.
Which one?
In the beginning of your talk.
Yeah.
That the superintegral is connected to the something. Theory, yes. Maybe your superintegrable formula, even for case n equal to 2, somehow can be applied to the.
Yeah, definitely, somehow, yes. So you see that to calculate this summa partial function, you can have any order of matrix. So if you think that you can put n equals 2 over here, the order of matrix. Yeah, you can use the formula that we found already over there. Yes. But if you think that our n is a big one, then it will be problematic.
Yeah, and maybe your formula for superintegrable somehow reformulated in terms of the model.
Yes, possible. Well, I haven't studied more details about this Kazakov-Milton model. Like, so there was like a proposal that how taking this kind of integral gives you some induced QCD. What is QCD? QCD is also like kind of some partition functions in a different form. So I personally didn't check that how taking these integrals in a simple case give you some give you some partition functions in QCD, but yeah, it might be also.
Okay.
Any more questions? Seems like Sasha is thinking about the questions now. Okay, so
Is there an analysis for other ensembles? Like, I mean, instead of unit integrating with the unitary matrix?
yes, okay, so matrix model can be think about in different ways. For example, the fast and simple example is Gaussian transmission. So if you, so that then you have some Gaussian potential over here. So these Gaussian transmission metrics are like more popular. They have studied a lot by many people. Yeah, so but we choose unitary because it makes a bit complicated and much less studied.
But I mean, different ensembles, different beta, orthogonal.
Okay, so what do you mean by orthogonal here?
I mean, you can integrate over orthogonal.
Yes, I think so. I think, but there will be a different model than in this case. But they will have a different structure over here also. So it should be a different model. Yeah, it probably exists. But we interested in just because of their appearance in physics, like this. So yes, there exists this kind of thing. And also, people say that this particular integral is somehow connected with some other two popular unitary integrals, which are called Kansavitch model and Gray's. I just forgot PDT double model or something like that. So they have a different structure over here, and there was a paper of Mironov and Semyonov. They found somehow the relation between these three unitary integrals in one language. So you can find it in this paper in the reference list. Just about this study. So, any more questions?
Thank you.